Something just entered our solar system, and astronomers cannot explain why it refuses to behave like anything we've ever seen before. Stay with me, because what scientists are tracking right now may change how we understand visitors from deep space forever. Not long ago, telescopes scanning the night sky picked up a faint moving point of light. At first, nobody panicked. Objects enter our solar system all the time. Comets drift inward from distant reservoirs of ice. Asteroids wander between planetary orbits. Space is busy, and astronomers are used to surprises. But this one felt different almost immediately. The discovery didn't come from a dramatic announcement or a press conference. It began quietly, inside automated sky surveys designed to catch tiny changes in motion. Systems connected to observatories around the world constantly compare images of the sky taken hours apart. Anything moving against the fixed background of stars gets flagged. That's how this object appeared. A slow shift, a faint signal. Just another candidate among thousands detected every year. Except when orbital analysts began running trajectory calculations, something strange showed up. The object wasn't following the gentle curved path expected from something born inside our solar system. Its speed was too high. Its angle was wrong. Its approach direction didn't match known comet families originating from the Kuiper Belt or even the distant Oort cloud. Within hours, additional observations were requested. Telescopes at the European Southern Observatory turned toward it. Follow-up measurements came from facilities linked to the Harvard-Smithsonian Center for Astrophysics. Independent confirmation arrived from observers using instruments in Hawaii near the Keck Observatory. The conclusion arrived quietly, but unmistakably. This object did not originate here. It came from interstellar space. Only twice before in human history had we confirmed such visitors. The first was Oumuamua in 2017, detected by the Pan-STARRS survey. The second was Comet Borisov in 2019, a more familiar icy traveler behaving exactly as physics predicted. Both objects passed through quickly, giving scientists only brief opportunities to study material formed around other stars. This new arrival immediately joined that rare category. But unlike Borisov, it didn't look like a comet. At this distance from the sun, a normal comet begins to wake up. Ice heats slightly. Gas escapes. Dust forms a faint, glowing cloud called a coma. Even weak activity becomes visible through modern instruments. Yet early images showed none of that. Just a sharp point of light. No fuzzy halo. No tail. No expanding cloud. Astronomers initially assumed activity would appear later as the object moved closer to sunlight. That assumption felt safe. Physics has rules, and those rules have worked for centuries. But days passed, then weeks. Still nothing. Around this time, orbital refinement teams working with NASA's Jet Propulsion Laboratory began publishing updated motion solutions. And that's when observers noticed something even harder to explain. The object was accelerating slightly. Not dramatically, not enough to alarm anyone at first, but enough that gravitational models alone couldn't perfectly account for its motion. Normally, comets accelerate because jets of evaporating gas act like tiny thrusters. Sunlight warms the surface, material escapes, and the escaping gas pushes the object gently off course. That process always leaves evidence. Gas signatures, dust trails, spectral fingerprints detectable by instruments like those used in Hubble spectrograph observations. This time, the motion changed, without visible exhaust. Imagine watching a boat change direction across still water without leaving ripples behind. That's the closest everyday comparison scientists could offer. At first, researchers assumed measurement error. That happens often. Space observations rely on extremely faint signals collected across enormous distances. A small calibration issue can mimic strange motion. So more telescopes joined the effort. The James Webb Space Telescope scheduled infrared observations to search for hidden heat signatures. Ground-based arrays compared brightness curves night after night. Older Arecibo legacy analysis methods were even revisited to rule out radar reflection assumptions used in past asteroid tracking. Every new dataset confirmed the same uncomfortable pattern. The object remained compact, inactive, and slightly off prediction. Now here's where things get interesting, and this is important to understand. Astronomy moves slowly because scientists distrust excitement. Extraordinary claims require boring confirmation. Nobody wants another false alarm built on incomplete data. But privately, discussions began spreading through research groups, because Oumuamua had shown similar unexplained acceleration years earlier. Harvard astrophysicist Avi Loeb famously proposed that radiation pressure acting on an unusually thin object could explain its motion. Others argued for exotic ice compositions like hydrogen or nitrogen that evaporate invisibly. The debate never fully settled. And now, another object was raising familiar questions. Two interstellar visitors showing behavior that didn't neatly match known comet physics. Coincidence? Maybe. But patterns make scientists uneasy. Right about here, about 2 minutes into understanding this story, I want to say something quickly. If you enjoy deep space investigations like this, liking and subscribing genuinely helps us keep digging into real research stories like this one. It tells YouTube these long-form science breakdowns matter, and it allows more time to go into finding and explaining discoveries like this properly. Because what happens next is where the mystery deepens. As tracking improved, analysts realized the object's incoming path did not align with the flat planetary plane most solar system bodies follow. It entered from a steep angle relative to the ecliptic, suggesting an origin shaped by gravitational events around another star system entirely. Somewhere, long ago, this object was likely thrown outward during planetary formation. A gravitational slingshot, a stellar close encounter. Perhaps even the chaotic birth of giant planets ejecting debris into interstellar darkness. For millions, maybe billions of years, it drifted alone between stars. Until now, Voyager 1 telemetry reminds us just how empty interstellar space truly is. Even traveling faster than any human-made spacecraft before it, Voyager moves through regions where particles are separated by vast distances. Temperatures approach absolute zero. Radiation slowly alters exposed surfaces. Anything surviving that journey must be extraordinarily stable, which raises another question scientists began asking. What kind of material allows an object to travel across interstellar space and still remain intact enough to reach another star system without breaking apart? That question still does not have a clear answer. And the closer this object moves toward the inner solar system, the stranger the data becomes. At first, nothing about the object demanded urgency. It moved silently, steadily, almost politely through the outer darkness beyond Jupiter's orbit. If you looked up from Earth, even through a powerful amateur telescope, you would see absolutely nothing unusual. No glowing streak, no dramatic tail. Just another invisible traveler crossing distances too vast for human intuition. But inside observatories, attention was growing. Every night, more measurements arrived. Light curves, position updates, spectral readings. Tiny fluctuations recorded by instruments designed to notice changes smaller than the width of a human hair seen from thousands of kilometers away. And slowly, the picture stopped making sense. Normally, when astronomers observe a comet approaching the sun, brightness increases in predictable ways. Ice begins turning directly into gas, carrying dust outward. The object grows hazy. Sunlight reflects differently as particles scatter light into space. This object refused to follow that pattern. Its brightness increased, but too smoothly. Almost mathematically smooth. Instead of the chaotic flickering expected from tumbling ice releasing uneven jets, the light reflected from its surface changed with strange consistency. Researchers at the European Southern Observatory compared the data against known comet models and found the variation unusually clean. Too clean. One astronomer described it privately as looking less like a dirty snowball and more like a polished fragment. That comparison spread quietly, because nature rarely polishes anything perfectly. Meanwhile, Teams connected to NASA's Jet Propulsion Laboratory refined rotational models. Every object spins. Asteroids wobble. Comets tumble unpredictably as gas eruptions push unevenly across their surfaces. Yet rotational analysis suggested something unexpected. The object appeared stable, not perfectly locked, but far less chaotic than expected for something that had supposedly wandered interstellar space for millions of years, enduring impacts, radiation damage, and gravitational disturbances. Stable rotation means structural strength. And structural strength raises uncomfortable possibilities. Around this time, infrared observations began arriving from the James Webb Space Telescope. Webb's instruments are sensitive enough to detect faint thermal emissions, the gentle warmth objects release after absorbing sunlight. Astronomers expected at least some detectable heat signature. Instead, readings came back unusually faint, which implied one of two things. Either the object reflected most incoming energy extremely efficiently, or it absorbed energy without re-radiating heat in ways scientists typically observe. Neither explanation fit comfortably within known comet behavior. The comparison to Oumuamua returned again. You may remember that Oumuamua also showed no visible tail despite measurable acceleration. Later studies suggested hydrogen outgassing could explain the motion without visible dust, but that explanation remains debated even today within the Harvard-Smithsonian Center for Astrophysics and other research institutions. Now scientists faced a similar puzzle. Another interstellar visitor, another absence of visible activity, another trajectory deviation, too small to panic over, yet too persistent to ignore. Then came the trajectory refinement update that truly shifted attention. As observational arcs lengthened, orbital analysts noticed the object's incoming velocity exceeded typical long-period comet speeds by a significant margin. Its motion relative to nearby stellar neighborhoods suggested it had not merely drifted slowly between stars. It had been moving fast, very fast, fast enough that gravitational capture by our sun was impossible. This was not an object settling into orbit. It was passing through a visitor entering and leaving on a one-time journey lasting only months, which meant humanity had limited time to study it. Global coordination intensified almost overnight. Observatories in Chile, Hawaii, Spain, and Australia synchronized observation windows. Even smaller university telescopes contributed positional measurements. Data pipelines fed continuously into shared databases used by planetary defense tracking systems originally designed to monitor potentially hazardous asteroids. And still, the mystery deepened. Spectroscopy, the science of splitting light into chemical fingerprints, began revealing surface information. Normally, comet spectra show clear signatures of water vapor, carbon monoxide, methane, or ammonia. Here, signals appeared muted. Weak traces existed, but nothing dominant. It was as if the object lacked the volatile richness expected from frozen primordial material. Some researchers proposed it might be unusually rocky. Others suggested cosmic radiation could have baked away surface ice during its interstellar journey, leaving behind a hardened crust. That explanation made sense, until motion data complicated things again. Because the slight acceleration persisted, something was still pushing it, and yet telescopes saw no plume, no jet, no escaping cloud. At Stanford, researchers revisited Ronald Bracewell's early concepts about detecting artificial objects through anomalous motion signatures, not because anyone believed this was technology, but because anomaly classification frameworks sometimes borrow ideas from outside standard planetary science. When nature behaves unexpectedly, scientists widen comparisons. That's how progress works. Still, caution dominated every discussion. Extraordinary interpretations were avoided publicly. Official communications described the object simply as an unusual interstellar body under continued observation. But internally, curiosity was growing stronger, because every known explanation required assumptions. Unusual composition, exotic ice chemistry, unknown structural strength, unseen gas release mechanisms. Each solution solved one problem while creating another. And then something subtle happened that few outside astronomy noticed. Background star measurements began showing tiny distortions during certain observation angles. Nothing dramatic, no cinematic gravitational bending visible to the eye. But precise imaging suggested faint irregularities in how light passed near the object's position. Gravitational lensing at this scale should have been impossible unless the object possessed more mass than brightness estimates suggested. That finding triggered reanalysis. Was the object darker than expected, larger than assumed, or composed of material reflecting almost no light at all? Suddenly, size estimates expanded. If reflectivity was extremely low, the object could be far larger than initial calculations indicated. A darker object appears smaller because it reflects less sunlight, which meant astronomers might not be tracking a small interstellar rock, but something significantly bigger moving silently through planetary space. And for the first time since its discovery, discussions shifted from curiosity to caution, because humanity had seen visitors before, but never one that resisted classification at every step. And as it continued its inward journey, approaching regions where solar radiation should finally force visible change, scientists prepared for the moment when physics would either reassert itself or fail again. As the object moved closer toward the inner solar system, astronomers reached what many quietly considered the moment of truth. Distance changes everything in space. Far from the sun, objects can remain frozen and inactive for millions of years. But once sunlight strengthens, physics usually takes over with ruthless predictability. Ice warms, gas escapes, surfaces fracture. Even ancient bodies that have slept since the birth of stars begin to awaken. This is the stage where every comet finally reveals itself. By the time objects cross the orbit of Mars, activity becomes undeniable. Even weak comets grow faint atmospheres visible through medium-sized telescopes. Dust spreads outward, forming the familiar glowing envelope humanity has associated with comets, since ancient civilizations recorded them as omens in the sky. So observatories waited, and watched, and measured. The sun's radiation increased exactly as expected. The object brightened slightly, but once again, the expected transformation never came. No coma formed, no tail appeared. Images captured through instruments at the Keck Observatory showed the same compact, unresolved point of light night after night. Follow-up confirmation from ESO facilities in Chile matched perfectly. Even sensitive long-exposure imaging designed to reveal the faintest dust clouds returned empty results. Astronomers began using a phrase rarely spoken early in investigations: persistent anomaly. At NASA's Jet Propulsion Laboratory, updated motion models now required a small non-gravitational force to explain trajectory drift. The acceleration remained subtle, thousands of times weaker than Earth's gravity, but its consistency ruled out random measurement error. Something was pushing the object, yet nothing visible was doing the pushing. The comparison to Oumuamua returned again, but this time with greater urgency. When that first interstellar visitor passed through in 2017, scientists had only weeks of usable observation time before it disappeared forever into darkness. Many questions remained unresolved simply because instruments were not ready. Now they were ready. The James Webb Space Telescope focused its infrared sensors toward the object, searching for hidden molecular signatures invisible to optical telescopes. Webb's sensitivity allows scientists to detect gases thinner than anything measurable from Earth's surface. If evaporation existed, Webb would see it. The results arrived gradually, and they complicated the mystery even further. No strong water vapor signature, no dominant carbon monoxide plume, no methane cloud, only faint, ambiguous signals hovering near detection limits. It was as if the object interacted with sunlight differently from known cometary material. Instead of erupting violently, its surface appeared almost resistant to heating. Imagine placing ice under a blowtorch and watching it refuse to melt. That was the uncomfortable analogy circulating among researchers. Some planetary scientists proposed an insulating crust formed during interstellar travel. Cosmic radiation over millions of years could chemically transform outer layers into carbon-rich compounds, dark, hardened shells capable of trapping volatile material beneath. Such crusts are theoretically possible, but models suggested they should eventually crack under solar stress. Still, nothing cracked. Meanwhile, brightness measurements revealed another subtle irregularity. The object reflected light unevenly across wavelengths, appearing darker in visible light, yet slightly brighter in specific infrared bands. That pattern hinted at an unusual surface composition, possibly metallic minerals, possibly carbon-based compounds, unlike typical comet dust, or something altered by processes rarely observed directly. Harvard-Smithsonian researchers compared spectral behavior against asteroid databases, comet archives, and even meteorite samples recovered on Earth. No perfect match appeared. Every comparison came close, but never aligned completely. Around this time, astronomers studying rotational dynamics noticed a slow change in spin rate, not chaotic tumbling, something gentler. A gradual adjustment consistent with continuous force acting over time, like a steady pressure rather than explosive jets. Solar radiation pressure became a serious candidate explanation. Photons from sunlight carry momentum. Over vast timescales, even light itself can push objects through space, but calculations showed a problem. For radiation pressure alone to account for observed acceleration, the object would need an extremely low mass relative to its surface area, almost like a thin sheet or highly porous structure. Natural objects rarely form that way and survive intact. Again, no one suggested artificial origins publicly. Scientists are trained to exhaust natural explanations first, but privately, the discussion expanded into unfamiliar territory. Because science advances not when answers appear, but when questions refuse to disappear. Then came one of the strangest observations yet. During a sequence of deep imaging sessions, background stars passing near the object's line of sight appeared fractionally dimmer than expected. The effect was tiny, detectable only through careful statistical comparison, yet it suggested the object absorbed light unusually efficiently, almost completely. Most celestial bodies reflect at least some portion of incoming light. Even charcoal reflects more than absolute darkness. But this visitor behaved closer to a near-perfect absorber, a moving shadow against the star field. That discovery forced astronomers to reconsider size estimates again. If reflectivity, known as albedo, was extremely low, then the object could be far larger than brightness alone implied, possibly kilometers across, possibly more. And suddenly the narrative changed. Humanity was no longer observing merely a curious interstellar pebble drifting through space. We might be witnessing a massive traveler ancient beyond comprehension crossing our planetary neighborhood for the first and only time in recorded history. Meanwhile, Voyager 1, now more than 24 billion kilometers from Earth, continues transmitting faint signals from interstellar space itself. Its telemetry reminds scientists how hostile that environment truly is. Radiation, dust impacts, and thermal extremes slowly degrade even human-engineered systems. Anything surviving that journey naturally must possess extraordinary resilience, which raised a quiet question spreading across observatories worldwide. What history does an object carry after wandering between stars longer than humanity has existed? What collisions did it survive? What systems did it once orbit? And why does it look untouched? As the object moved inward, crossing thresholds where solar forces should finally dominate, anticipation grew across the astronomical community, because soon, physics would deliver a final verdict. Either activity would begin, or the anomaly would deepen beyond anything previously recorded. And the closer it came to the sun, the more scientists realized something unsettling. Instead of becoming easier to explain, the object was becoming harder to understand. By now, the object was no longer just another entry in an astronomical catalog. Quiet alerts had spread across research networks, and observation time, one of the most valuable resources in modern science, was being reshuffled to prioritize continued tracking. That alone told a story. Large observatories do not interrupt scheduled programs lightly. Nights are planned, months or even years in advance. Entire research careers depend on those observation windows. Yet telescope time from facilities connected to the European Southern Observatory, the Keck Observatory, and multiple university arrays began shifting toward this single moving target because something subtle had changed. The trajectory deviation was growing clearer. Earlier measurements showed only slight mismatches between predicted and observed motion. Now the difference accumulated night after night. When analysts at NASA's Jet Propulsion Laboratory updated orbital solutions using extended tracking data, the residual errors refused to disappear. Gravity alone could no longer explain the path. The object was drifting outward faster than expected after solar approach, gaining velocity in a way that should require energy input. Not explosive energy, not sudden thrust, but steady acceleration. And steady acceleration demands explanation. In normal comets, this behavior comes from asymmetric outgassing jets of vapor, acting like microscopic rocket engines. Even weak activity creates measurable force over time. But once again, imaging showed no expanding gas cloud, no dust stream, no detectable plume. It was like watching motion without cause. Astronomers began performing elimination tests. Could solar-wind interactions be responsible? Charged particles streaming from the sun can influence extremely small bodies, but calculations showed the object was too massive for solar wind pressure alone. Could hidden jets be directed away from Earth, escaping detection? Possibly. Yet infrared instruments aboard the James Webb Space Telescope should still detect escaping molecules regardless of direction. Webb saw none strong enough. Could gravitational interaction with an unseen fragment or companion object explain motion? Searches revealed nothing nearby. Each explanation collapsed under observation. Meanwhile, something else began attracting attention: the object's orientation relative to the sunday. Its long axis appeared to adjust slowly during travel, maintaining a configuration that maximized exposure to sunlight. Not perfectly aligned, but statistically biased toward orientations producing greater radiation interaction. Natural tumbling bodies rarely behave that way for long periods. Rotational chaos usually dominates. Yet modeling teams found rotational damping occurring faster than expected, almost as if internal mass distribution resisted instability. That finding sparked new debates about structure. Perhaps the object was unusually dense in some regions and hollow in others. Perhaps ancient collisions reshaped it into something aerodynamically stable under photon pressure. Some researchers compared possibilities to fragments produced during planetary tidal disruption events, pieces torn apart by gravity during close stellar encounters. Others revisited exotic ice theories once proposed for Oumuamua, including hydrogen or nitrogen ice, capable of sublimating invisibly. But those models faced growing challenges. Such materials would erode rapidly under solar heating, dramatically altering brightness over time. Brightness remained steady, too steady. At the Harvard-Smithsonian Center for Astrophysics, statistical modeling teams examined population expectations for interstellar objects. Theoretical estimates suggested many such travelers should pass through our system over cosmic timescales. Yet detection rates remained low, which raised another possibility. Perhaps most interstellar visitors are dark, extremely dark, hard to detect unless passing unusually close to the sunday. If true, humanity may have missed thousands before developing modern sky surveys. That thought changed perspective entirely. Instead of witnessing something unique, we might simply be seeing one of the first examples clearly enough to study. Still, the mystery persisted. Then global attention quietly expanded beyond professional astronomy. Planetary defense monitoring systems originally built to track near-Earth asteroids incorporated the object into long-term simulations, not because it posed danger, but because its motion resisted simplified modeling. When predictions struggle, caution follows. Data pipelines cross-checked measurements against historical archives. Analysts revisited Arecibo legacy datasets, searching for faint earlier detections before discovery confirmation. None appeared. The object had entered observable range only recently, which meant humanity was seeing it for the first time, and likely the last. As weeks passed, media outlets began noticing scientific chatter. Headlines cautiously described an unusual interstellar visitor. Public fascination returned. echoing global curiosity from the Oumuamua discovery years earlier. But among scientists, excitement mixed with restraint, because the closer the object approached perihelion, its nearest point to the sun, the greater expectations became. This would be the decisive phase. Solar heating would reach maximum intensity. Any hidden volatile material should erupt dramatically. Dust should scatter sunlight. Activity should finally expose composition and confirm natural origins beyond doubt. Everything depended on that moment. And observatories prepared accordingly. High-cadence imaging campaigns began. Spectrographs ran nightly. Webb scheduled repeated infrared passes. Even smaller observatories contributed continuous brightness monitoring to capture rapid changes. The entire astronomical community waited for physics to reassert its familiar rules. But as perihelion approached, the object remained calm. No explosion of activity. No sudden transformation. Just the same dark traveler sliding silently past the Sunday. And for the first time since discovery, some researchers admitted privately that the mystery might not resolve cleanly before the object departed forever, because time was running out. Every hour carried it closer to escape velocity toward the outer darkness beyond Neptune, where sunlight weakens and observation becomes nearly impossible. Soon, humanity would lose its chance to ask questions directly. And the most unsettling possibility began settling in. We might watch it leave, without ever knowing exactly what it was. Perihelion arrived almost quietly. There was no visible spectacle in the sky, no blazing streak for humanity to witness with naked eyes. The event unfolded entirely through numbers arriving across screens in observatories scattered around the planet, streams of telemetry, updated brightness, measurements, spectral readings collected photon by photon from millions of kilometers away. This was the moment everything was supposed to make sense. Solar radiation now reached its strongest intensity. Temperatures on exposed surfaces should have risen sharply. Any remaining volatile material, frozen gases trapped beneath ancient crust, should finally erupt outward. Astronomers expected transformation. Instead, they watched consistency. The object rounded the sun and emerged on the outbound leg of its journey, looking almost identical to how it entered. Still compact, still dark, still without a visible tail. Images captured through large aperture telescopes showed no expanding coma, no scattering dust plume. Even sensitive stacked exposures designed to reveal structures thousands of times fainter than the object itself returned empty backgrounds. It had passed the sun, and nothing dramatic happened. That alone would have been strange enough. But the orbital data arriving in the days that followed introduced the most unsettling detail yet. The acceleration increased. Not suddenly, not violently, but measurably stronger than before perihelion passage. Analysts at NASA's Jet Propulsion Laboratory recalculated trajectory models repeatedly, checking for computational errors, gravitational perturbations from planets, relativistic corrections, every known factor influencing motion. Each revision produced the same outcome. A non-gravitational force remained present, and it was acting after solar heating should have peaked. If sublimation drove acceleration, activity should weaken as distance from the sun increased. Yet motion suggested continued push, like momentum supplied from somewhere unseen. At this stage, scientists moved carefully in public communication. Official statements described the object as exhibiting non-standard cometary behavior. That phrase may sound mild, but within scientific culture, it carries weight. It means known explanations are insufficient, but conclusions remain open. Meanwhile, theoretical papers began appearing almost immediately. Some researchers proposed ultra-dark carbon surfaces absorbing sunlight and re-emitting energy directionally through thermal radiation, a process known as the Yarkovsky effect. Others suggested trapped gases escaping through microscopic pores, too small to form visible jets. Both ideas remained possible. Neither matched observations perfectly. The James Webb Space Telescope continued infrared monitoring, searching for thermal asymmetry that might reveal hidden energy release. Webb's instruments detected surface temperatures lower than expected for an object receiving direct solar illumination. Lower temperatures implied efficient heat redistribution or reflection properties not commonly observed in cometary nuclei. Again, explanations multiplied without resolution. At the European Southern Observatory, astronomers examined polarization data measurements, describing how reflected light waves align after interacting with surfaces. Results hinted at unusual surface texture, potentially smoother or more uniform than typical space-weathered rock. Nature rarely produces uniformity across kilometer scales, but space also surprises us constantly. As debates continued, another realization settled across the astronomical community. The object was leaving faster than anticipated. Every passing week reduced resolution. Brightness declined gradually as distance increased. Soon, even the largest telescopes would struggle to maintain detailed observations. Humanity's window was closing. And that realization changed the emotional tone surrounding the discovery. Because astronomy often operates on patience, stars evolve slowly. Galaxies collide over billions of years. Most mysteries remain available for future generations to revisit. Interstellar visitors are different. They arrive once, they leave once, and then they are gone forever. Voyager 1, drifting outward since 1977, will someday become exactly such an object for another civilization. A faint, artificial speck, crossing alien skies long after humanity itself changes beyond recognition. That thought lingered among scientists studying this traveler. Somewhere, perhaps millions of years ago, this object passed near another star. Perhaps worlds existed there. Perhaps civilizations looked outward just as we do now, unaware that fragments from their system would wander endlessly through the galaxy. Now it had visited ours, and soon it would disappear into darkness again. As outbound tracking continued, acceleration slowly diminished, though never entirely vanished within measurement uncertainty. Without extended observation time, determining the exact mechanism became impossible. The mystery would remain partially unresolved. Papers would be written, models debated. Future telescopes, including the Vera Rubin Observatory, may discover many more interstellar visitors, allowing comparison and statistical understanding. But this particular object would become something else, a reference point, a reminder that the solar system is not isolated, that material and perhaps histories move constantly between stars, that our cosmic neighborhood is part of a much larger exchange happening across the Milky Way, and perhaps most importantly, that nature still holds behaviors we do not fully understand. As the object faded beyond reach, one truth became unavoidable. The universe had presented humanity with a question, and then taken the answer back with it. As the object continued its silent departure, something unexpected happened on Earth. The urgency faded, not because the mystery had been solved, but because observation slowly gave way to distance. Night after night, the signal weakened. Exposure times grew longer. Data arrived with larger uncertainty margins. Eventually, tracking required the largest instruments humanity possessed just to maintain visual confirmation, and with that fading signal came reflection. Astronomy has always lived with unfinished stories. Entire generations dedicate their lives to studying phenomena they know they will never see resolved. Stars collapse beyond our reach. Galaxies evolve too slowly for human timelines. Even Voyager 1, still transmitting from interstellar space, sends information that future scientists will interpret long after its mission ends. This visitor joined that category. Not solved, not dismissed. Simply incomplete. Yet the deeper impact was already unfolding, because discoveries like this quietly reshape how scientists think about the galaxy itself. For most of history, humanity imagined planetary systems as isolated islands, each star surrounded by material forever bound to its birthplace. Modern astrophysics tells a different story. Planetary systems leak. During formation, massive planets fling debris outward. Stellar encounters disturb distant reservoirs like the Oort cloud. Supernova shockwaves rearrange gravitational boundaries. Over billions of years, fragments are exchanged between stars like drifting messages in an ocean too vast to see all at once. Every interstellar object is evidence of that exchange. a physical sample from another solar system passing briefly through ours. And if objects can travel between stars naturally, then chemistry travels too. Water-bearing rocks, organic molecules, carbon compounds, possibly even the raw ingredients required for life. Researchers at the Harvard-Smithsonian Center for Astrophysics have long explored the possibility that planetary building blocks migrate across stellar neighborhoods. Some theories suggest early Earth itself may have received complex organic material formed elsewhere in the galaxy. In that sense, visitors like this are not intruders. They are participants in a cosmic circulation system billions of years old. But this object added another layer to that realization, because it resisted easy classification. It reminded scientists that assumptions based on local experience may not represent universal rules. Our solar system provides only one example among hundreds of billions in the Milky Way. Materials formed around other stars may behave differently under radiation, pressure, or chemical history unfamiliar to us. The universe may produce structures we simply have not encountered often enough to recognize. And that realization humbles science in the best possible way. At conferences and research discussions, astronomers began shifting conversation away from what the object was, toward what future discoveries might reveal. The upcoming Vera Rubin Observatory, designed to scan the entire visible sky repeatedly, is expected to detect interstellar visitors far more frequently. Instead of rare events separated by years, dozens may soon appear annually. Patterns will emerge. Comparisons will become possible. Mysteries that once stood alone may form families of behavior. And perhaps this object, strange as it seemed, will someday look ordinary within a much larger data set. But for now, it remains singular. A traveler, older than humanity's written history. A fragment shaped under another sun. A reminder that our solar system is not a closed story. As the final confirmed observations arrived, astronomers calculated its outbound trajectory. Within months, it would pass beyond the range of meaningful spectroscopy. Within years, it would fade below detectability entirely. Eventually, it would rejoin interstellar darkness. No mission could chase it. Even humanity's fastest spacecraft would require decades merely to approach its path. The encounter was observational, only a distant handshake between star systems. And then it was over. Yet something lingered, because every scientist involved understood a quiet truth. We are living at the beginning of interstellar astronomy. For the first time in history, humanity possesses instruments capable of detecting objects born around other stars in real time. What once would have passed unnoticed now becomes measurable, analyzable, and deeply personal. The night sky is no longer static. It is traffic, movement, exchange, stories crossing unimaginable distances, and somewhere, far beyond Neptune's orbit now, this mysterious object continues its journey unchanged by our curiosity, unaware of our debates, carrying whatever history shaped it long before Earth formed oceans, or life began breathing. It came without announcement. It left without explanation. But it changed something subtle in how we look upward, because the next visitor may arrive tomorrow, and the next one after that, each carrying pieces of distant worlds, ancient collisions, forgotten planetary systems, fragments of a galaxy constantly reshaping itself. We used to think space between stars was empty. Now we know it is simply quiet. Long before this object ever entered our sky, humanity had already been preparing, without realizing it, for discoveries exactly like this. For decades, astronomers suspected interstellar visitors must exist. The math made it unavoidable. Every young planetary system forms in chaos. Giant planets migrate. Smaller bodies collide and scatter. Gravitational encounters fling debris outward at escape velocity, ejecting fragments permanently into the galaxy. Our own solar system likely expelled trillions of objects during its early history. Some of those fragments are still traveling today. Some may already be passing through distant star systems right now. And somewhere, unimaginably far away, another civilization, if one exists, might someday detect a tiny artificial object drifting silently past their star. Voyager, a machine carrying sounds of Earth, launched in 1977, now moving through interstellar space faster than almost anything humanity has ever built. NASA's Deep Space Network still listens for its faint radio whisper, a reminder that interstellar travel, even unintentionally, has already begun. That perspective changed how scientists began thinking about this mysterious visitor. Because if natural objects cross between stars regularly, then interstellar space is not merely emptiness. It becomes a transport system, slow, cold, but persistent. Material travels. Chemistry travels. Information encoded in structure travels. And sometimes, those travelers arrive intact enough to be studied. As new observation campaigns continued, researchers began analyzing the object's surface evolution after perihelion. Normally, solar heating leaves scars. Fresh fractures appear. Reflectivity changes as buried material becomes exposed. But long-term brightness monitoring suggested remarkably little alteration. Weeks after closest approach, reflected light characteristics remained consistent within measurement uncertainty. That implied extraordinary durability. One working hypothesis proposed that prolonged exposure to cosmic radiation during interstellar travel could create a chemically altered outer shell, sometimes called an irradiation mantle. Over millions of years, energetic particles rearrange molecular bonds, producing dense carbon-rich layers similar to hardened asphalt. Such mantles could protect internal material from rapid sublimation. But even this explanation struggled to account for the continued absence of detectable debris. At the Keck Observatory, high-resolution spectroscopy attempted to isolate faint molecular signatures, trailing behind the object's path. Researchers searched for ionized gases, dust grains, anything indicating interaction with solar wind. Results remained frustratingly inconclusive. If material escaped, it did so below detection thresholds, or in forms not easily recognized. Meanwhile, orbital analysts began reconstructing the object's incoming motion relative to nearby stellar neighborhoods. By reversing trajectory calculations, astronomers estimated its origin direction somewhere toward a dense region of the galactic disk, rich in older stars. Pinpointing a parent system proved impossible. Over millions of years, gravitational interactions blur origins beyond recovery. Still, statistical models suggested it likely formed around a star older than our Sunday, which introduced another fascinating implication. This object may predate Earth itself. Imagine that for a moment. Before Earth cooled, before oceans formed, before life emerged, this traveler may already have been wandering between stars. That realization transformed the emotional weight of observation. Scientists were not merely studying an astronomical curiosity. They were examining a relic from another planetary history, a survivor from an environment humanity may never directly see. And yet, despite its age and journey, the object displayed mechanical calmness in motion that continued to puzzle dynamicists. Rotation remained stable, acceleration remained smooth, surface behavior remained restrained. The absence of chaos became its defining characteristic. Nature usually leaves fingerprints of violence, impacts, fractures, asymmetry. Most asteroids resemble shattered rubble piles, barely held together by gravity. This object behaved more like a coherent body. Some researchers suggested it might be monolithic, a single solid fragment rather than an aggregate of debris. Others proposed compression under extreme tidal forces during ejection could have fused material unusually tightly. Both ideas remained plausible, neither fully satisfying. Then another subtle anomaly entered discussion. Radio observations searching for natural emissions detected nothing unusual, which was expected. But the silence itself reinforced how little interaction the object appeared to have with surrounding space. No plasma wake, no detectable ion tail, minimal interaction signatures with solar wind. It moved through space almost cleanly, like a stone passing through still air. Around this time, comparisons expanded beyond comets entirely. Planetary scientists began examining whether the object might resemble fragments produced during planetary crust, stripping events, pieces torn from rocky worlds during catastrophic collisions. Such fragments could possess unusual density and surface properties. But again, confirmation remained out of reach. Because distance was growing, Every day, the object traveled millions of kilometers farther away. Even light itself required longer to return information. Signal strength weakened. Noise increased. Precision faded. Astronomy was slowly losing its grip on the mystery. And that loss created urgency not for answers but for understanding what questions to ask next time. At conferences, discussions increasingly focused on readiness, future detection networks, faster classification pipelines. Dedicated interstellar interception mission concepts began resurfacing spacecraft designed to launch rapidly toward incoming visitors before they escape. NASA engineers and international collaborators have studied such missions theoretically for years, though none yet exist operationally. This object arrived too soon, but the next one might not. The realization settled quietly across the scientific community. Humanity had just experienced a rehearsal, a preview of a new era in astronomy where visitors from other star systems become observable events rather than historical accidents reconstructed after disappearance. And perhaps most profoundly, it reminded observers of something deeply human. We are no longer confined to studying only our cosmic backyard. The galaxy is beginning to introduce itself, and sometimes introductions are brief, a passing shadow, a moving point of light, a mystery that arrives, challenges understanding, and departs before certainty can catch up. Out beyond the orbit of Saturn now, fading slowly into darkness, the object continued onward, unchanged, indifferent, carrying whatever story shaped it across distances so vast that even imagination struggles to follow. And somewhere ahead of it lies another star, another system, another sky that may someday notice its passage, just as we did. As the object faded farther from the sun, the conversation surrounding it began to split into quiet camps. This happens often in science, when observations refuse to settle cleanly into one explanation. Not arguments in the dramatic sense, but differences in emphasis. Different groups looking at the same data and asking slightly different questions. One camp believed the mystery would eventually dissolve into familiarity. History supports that view. Many cosmic puzzles once appeared impossible, until improved instruments revealed ordinary mechanisms hiding beneath limited data. Pulsars were once suspected to be artificial signals before neutron star physics explained their precise timing. Quasars baffled astronomers for years before supermassive black holes entered the picture. From this perspective, the object's strange behavior simply pointed toward chemistry or structure humanity had not yet studied closely. Perhaps an exotic combination of frozen nitrogen and carbon compounds. Perhaps material forged under pressures, unlike anything common in our solar system. Perhaps billions of years of cosmic radiation had transformed its outer layers into something rare but natural. Given enough future discoveries, this visitor might eventually look typical, but another group focused less on explanation and more on implication, because even if every anomaly ultimately proves natural, the pattern itself matters. Two confirmed interstellar objects within a few years, both displaying unexpected behavior, suggested humanity's previous assumptions about such visitors may have been incomplete. Our models were built from observing objects born around our own Sunday. But other stars form planets differently. Different chemical abundances, different stellar radiation environments, different gravitational histories. If planetary systems across the galaxy produce objects unlike ours, then interstellar space may contain entire categories of material we have never encountered before. In other words, the mystery might not lie in this object alone. It might lie in our expectations. Meanwhile, researchers working with long baseline observational archives began comparing the object's motion against simulations of galactic dynamics. By tracing backward through stellar movement models, they attempted to estimate how long it had traveled between stars. The answer stretched imagination, likely tens or hundreds of millions of years, possibly longer. During that time, it would have crossed spiral arms of the Milky Way, passed through regions dense with newborn stars, survived encounters with cosmic radiation fields stronger than anything inside planetary systems. Every kilometer of its surface recorded history older than humanity's species. And yet, all that history revealed itself only as faint reflected sunlight captured by telescopes on one small planet orbiting one ordinary star. There is something humbling about that scale mismatch. Around this stage of observation, astronomers also considered another question rarely discussed outside specialist circles: detection bias. We only see what our instruments allow us to see. Before modern sky surveys like Pan-STARRS and upcoming systems such as the Vera Rubin Observatory, objects like this would have passed entirely unnoticed. For billions of years, interstellar travelers may have crossed through our solar system without leaving any trace in human awareness. How many arrived before telescopes existed? How many passed during the age of dinosaurs? How many move through space right now beyond our ability to detect? The realization transformed the event from a singular mystery into evidence of a hidden population. Our solar system may experience interstellar visits far more often than previously believed. We are simply learning how to notice them. At NASA's Jet Propulsion Laboratory, simulation teams began incorporating interstellar object encounters into long-term solar system evolution models. These visitors pose no threat in most cases, yet their presence offers rare opportunities: physical samples of other star systems delivered freely by gravity itself. Future missions may attempt interception. Concept studies already exist proposing rapid response spacecraft equipped with solar sails or nuclear electric propulsion, capable of chasing incoming objects within months of discovery. Such missions would allow direct measurement rather than distant observation. But technology has not caught up yet. This object arrived during the transition period when humanity could see interstellar visitors, but not yet reach them. So astronomers watched, measured, learned what they could, and accepted the limits imposed by distance. As months passed, detection required stacking dozens of exposures together. Signal-to-noise ratios dropped. Measurement uncertainty widened. Eventually, only the largest observatories could still confirm position. The mystery began slipping away into statistics. And something interesting happened psychologically among researchers: relief mixed with disappointment. Relief because unresolved anomalies no longer demanded daily explanation. Disappointment because unanswered questions remained permanently unanswered. Science prefers closure. The universe rarely provides it. Yet even without definitive answers, the object accomplished something profound. It forced refinement of detection techniques, improved coordination between observatories, expanded theoretical frameworks describing planetary formation across the galaxy. And perhaps most importantly, it changed expectation. The next interstellar visitor will not arrive as a shock. It will arrive as anticipated company. Somewhere beyond Neptune now, sunlight weakening behind it, the object continued outward, its acceleration gradually blending back into gravitational motion alone, as measurement precision fell below certainty. Soon, it would become indistinguishable from background darkness. Another silent traveler returning to interstellar space. But its passage left behind something lasting, not proof of anything extraordinary, not confirmation of exotic theories. Something quieter. Evidence that our solar system is part of an active, connected galaxy, where material moves freely between stars, carrying unknown histories from places humanity may never see directly. And the next time astronomers notice a faint moving point against distant stars, they will look closer, sooner, and with very different expectations. By the time the object moved beyond the comfortable reach of continuous observation, something subtle had changed in the way astronomers talked about the sky itself. For centuries, the solar system was treated as a contained environment. Planets, moons, comets, and asteroids belonged here. They formed together, evolved together, and remained gravitationally bound to the sun, like members of a single family. Interstellar space was imagined as separation, vast emptiness dividing star systems into isolated islands. But discoveries like this quietly dissolve that idea, because what astronomers were now witnessing was exchange. Not metaphorical exchange, but physical movement. Matter crossing stellar boundaries without permission, without intention, guided only by gravity and time. The galaxy behaves less like scattered islands and more like an ocean filled with drifting currents. Stars form. Planets collide. Fragments escape, and those fragments travel until another star briefly captures their path. The object that passed through our system became evidence of that process happening in real time. And once scientists began thinking this way, older mysteries started looking different too. Meteorites found on Earth contain isotopic ratios suggesting material older than the Sun itself. Tiny grains embedded in primitive rocks, pre-solar grains formed around ancient stars long before our solar system existed. Laboratories studying these particles confirmed that matter from distant stellar explosions already resides beneath our feet. We have touched interstellar material before. We simply didn't watch it arrive. Now humanity has crossed into a new phase, observing the journey rather than discovering the leftovers. At institutions like the Harvard-Smithsonian Center for Astrophysics and research groups, collaborating with NASA's Jet Propulsion Laboratory, discussions turned toward frequency estimates. Updated models suggested interstellar objects might enter the inner solar system far more often than once believed, perhaps several per year, most too small or dark to detect with current technology. That realization reframed the mystery again. This visitor may not have been rare, only visible, and visibility changes perception. Consider how many phenomena seemed non-existent before instruments evolved enough to reveal them. Exoplanets were once theoretical. Now, thousands are catalogued. Gravitational waves were predicted for a century before detectors finally confirmed them. Even black holes moved from speculation to imaging within a single human lifetime. Interstellar astronomy may be following the same path. What appears mysterious today may become routine tomorrow. Still, this object retained its peculiar status because of timing. It arrived during humanity's technological adolescence, advanced enough to detect anomalies, yet not advanced enough to investigate directly. We could see, but not touch. That limitation shaped the emotional tone surrounding final observations. Astronomers scheduled farewell tracking sessions almost ceremonially. Large telescopes gathered final positional measurements, squeezing remaining data from fading light. Teams compared final brightness curves against discovery records, searching for any late transformation. None appeared. The object departed as it arrived, silent, unchanged. And in that consistency lay perhaps its greatest lesson. Nature does not owe explanation within human timelines. Sometimes discovery means accepting uncertainty rather than conquering it. Meanwhile, discussions expanded beyond astronomy into planetary science and astrobiology. If material travels freely between star systems, then chemical complexity may spread throughout the galaxy more efficiently than once assumed. Organic molecules detected in interstellar clouds already demonstrate that chemistry capable of supporting life forms naturally in space. Objects like this could act as carriers, protecting compounds during long journeys before depositing them into new planetary environments. The idea is known as panspermia, controversial, debated, but scientifically explored for decades. No evidence suggests this visitor carried life, but its mere existence strengthens the mechanism by which ingredients move between stars. Life, if it arises frequently, may not remain confined to its birthplace. It may travel, slowly, accidentally, persistently, and suddenly the mystery becomes larger than one object's strange motion. It becomes a question about connection across cosmic distances. As tracking capability finally diminished, the object's position uncertainty widened beyond meaningful analysis. Eventually, updates slowed. Observation notices stopped appearing. Databases marked it as outbound, future visibility unlikely. The scientific world moved on, as it always must. New discoveries replaced old questions, yet something remained behind, not data, but perspective. Humanity had watched a visitor from another star system pass through our neighborhood in real time, not imagined, not inferred. Observed directly using instruments built by generations of curiosity. And despite all our technology, the encounter ended the same way ancient skywatchers experienced comets thousands of years ago. A light appeared, a mystery formed, and then it vanished. Except now, instead of fear or superstition, the disappearance left curiosity sharpened rather than satisfied. Because next time, we will be ready sooner. Next time, detection networks will respond faster. Next time, humanity may attempt pursuit. Somewhere in mission design labs, Engineers are already sketching concepts inspired by encounters like this spacecraft, waiting on standby for the next interstellar arrival. The galaxy is no longer distant background scenery, it is sending visitors. And sooner or later, one will arrive close enough, slow enough, predictable enough, for humanity to meet it face to face. The moment that changed everything did not arrive with panic or celebration. It came quietly, buried inside the final consolidated datasets compiled after months of observation. When astronomers compared the object's entire journey from discovery to departure, one realization became unavoidable. Every stage where physics was expected to simplify, the mystery had instead preserved it. Before solar approach, scientists assumed inactivity was temporary. After perihelion, they expected confirmation of ordinary comet behavior. During departure, they anticipated fading irregularities caused by measurement limits. None of those expectations fully materialized. The object entered our solar system behaving unlike a traditional comet. It passed the sun without dramatic transformation, and it exited still carrying motion characteristics that resisted complete explanation. No catastrophic discovery, no proof of anything artificial, but something just as important, a boundary had shifted. For the first time, humanity watched an interstellar visitor closely enough to realize how little experience we truly have with material born around other stars. The anomaly was not that the universe behaved strangely. The anomaly was our assumption that it should behave familiarly. Data reviewed across institutions from NASA's Jet Propulsion Laboratory to observational teams linked with the European Southern Observatory and analysis groups referencing Hubble's spectrograph archives pointed toward the same conclusion spoken carefully among scientists. We are entering an era where the solar system is no longer isolated science. It is an intersection. The climax of this story was never the object itself. It was recognition. Recognition that our sun moves through a galaxy filled with travelers. Recognition that planetary systems exchange fragments constantly. Recognition that the next mystery may already be on its way while we are still debating the last one. The visitor did not reveal its origin. It did not explain its structure. It did not wait for humanity to understand it. It simply passed through following the same cosmic laws that have guided matter across the Milky Way for billions of years, leaving us with better questions than we had before. And perhaps that is how discovery truly works. Not answers arriving fully formed, but horizons expanding just enough to show how much remains unseen. Now the object continues outward, sunlight fading behind it, returning to interstellar darkness where distances stretch beyond imagination. Somewhere ahead lies another star system, another sky, another possible civilization that may one day notice a faint moving point and wonder where it came from, just as we did. The mystery is unfinished. The story is ongoing. Because the galaxy is not quiet anymore, we have learned how to listen. If you want to keep following discoveries like this and be here when the next interstellar visitor appears, watch the next video on your screen and subscribe so you don't miss what the universe sends our way next.